Good afternoon, students. We will be doing today the next unit. Okay, this part we have already done. Let me show you. So this part we have already done in the last class. So today we are moving to carbonyl compounds, and in today's class we will be only covering a very small portion. Though it looks to be very small portion, but it is, however, not that. Anyway, let me show you. So this is the part we will be doing today. We will be concentrating on structures, reactivity, preparation, and properties. Okay, so let us start. First, we will do structure of carbonyl compounds. Carbonyl compounds are present in both aromatic and aliphatic compounds, and it is mainly having a functional group C double bond O. Now C is here sp2 hybridized, and there is a pi bond. Okay, so it is having a planar structure, and the bond angle is 120 degree. These are horizontal overlap. Okay, that is the sigma bond. These are the sigma bonds. There are 3 sigma bonds and one pi bond. So 3 sigma bonds means it is S, P and P, that is sp2 hybridized, and 1 p orbital, that is third p orbital, is going for vertical overlap. Okay, so this is what we see here, and this particular bond is highly polar, and this is the polar nature, and we have here our C double bond O, and it is oxygen is highly electronegative, and therefore it is getting a partial negative charge, and carbon is getting a partial positive charge. Okay. There are several compounds which has such a group. Okay, C double bond O. First it is aldehyde and ketone. Then we have, if it is only R is replaced by H, we call it as formaldehyde, or you call it as methanol. Okay, carboxylic acid groups are also having C double bond O group with along with OH group, C double O H group, ester, amides, enones. Okay, just see what is the structure of enone. Enone is having a ketonic group and an ene that is alkene group. Alkene group and ketonic group together we call it as enone. Acyl halide, and the ketonic group, carbonyl group along with halide, we call it as an acyl halide, and acid anhydride. Okay, this is the acid anhydride group. So let us first see the properties of the main compound, that is aldehydes and ketones. Aldehydes and ketones are polar compounds, polar molecules, because C double bond O has a dipole moment. Now if you compare the acetone with propene or isopropanol, you will find acetone is the most polar, and it is having the approximately quite a high boiling point compared to propene. Why? Because propene is non-polar. Okay, it is almost non-polar because it is having a dipole. It is having a bond between C and C. Okay, because of its dipole nature, so many acetone molecules can associate without forming any hydrogen bond. Acetone or ketone and aldehyde are such compounds which do not have any H bonded to an electronegative atom, oxygen. Okay, so therefore they are having hydrogen, but they are not having any hydrogen which can form hydrogen bond. Okay, so therefore if you look into the structure of isopropanol, you will find the carbon is bonded to one oxygen via a sigma bond, and the oxygen is bonded to a hydrogen. So therefore this is capable of forming hydrogen bonding, and therefore a large number of isopropanol molecules associate with each other, forming hydrogen bond. Okay, so therefore the boiling point of isopropanol is very high. You can see here it is 82.3 degrees centigrade, whereas its dipole moment is only 1.7 dBi. Whereas in case of acetone, it is having a dipole moment 2.7 dBi, because it is bonded to, the carbon here is bonded to an oxygen via double bond, means a sigma bond and a pi bond. And pi bond, as you know, is quite a weaker bond, and the oxygen, which is more electronegative, can pull the electrons of this bond towards itself, making it a negative charged species. Okay, so therefore the dipole moment is quite high here, and whereas the boiling point is quite low. Okay, so let us look into the next point. Their polarity makes aldehyde and ketones have higher boiling point than alkenes. This I have already explained you. Aldehydes and ketones are not having any hydrogen bond donor. They cannot form they cannot donate a proton. Therefore, they have lower boiling point than alcohol of similar molecular weight. This also has been discussed. Aldehydes and ketones are hydrogen bond acceptor. Okay, this makes them have considerable solubility in water. So the hydrogen and of water can make a kind of it can accept the hydrogen because of the presence of oxygen, and therefore it is able to make itself soluble in water. Now let us look into the next point, that is reactions of aldehydes and ketones. Now if you look into the proper structure of aldehydes and ketones, you will find there are two active groups. Okay, one is the carbonyl group and another is the alpha carbon. Okay, alpha carbon is the adjacent carbon to the functional group. Now these two are the reaction sites. Okay, reaction sites. Now carbonyl group can have three main reactions. Okay, reaction with acid addition reaction, and oxidation reaction. First, let us see the addition reaction, how it gets added. Now, whenever you take a molecule, the molecule will have a positive part and a negative part. Supposing here E is the positive part and Y is the negative part of a particular molecule. Now, the negative part will get added to carbon, which is partially positive charge, and the positive part will get added to the oxygen, which is having a partial negative charge. So addition reaction can occur in two different mechanisms: base catalyzed addition under the influence of a basic or neutral condition, and acid catalyzed addition, that is under the influence of an acid. Oxidation, how the oxidation happens? Oxidation can happen in such a way that we have different oxidizing agents. Okay, but remember one thing, it's very important. If you take an aldehyde, if you go for an oxidation with a general oxidizing agent like K2Cr2O7, KMnO4, like those, okay, it will directly go into the carboxylic acid group. Okay, aldehyde will get oxidized to carboxylic acid group. Whereas if you take a second degree alcohol, it will oxidize itself to ketones. Okay, whereas primary alcohols will oxidize itself to a carboxylic acid group. So we have to be choosy about oxidizing agent to form aldehyde from a primary alcohol, because if you take a primary alcohol, it will be uncontrollably getting oxidized to carboxylic acid group with a general type of oxidizing agent. Okay, next is what is the basicity of aldehydes. Okay, reactions which occur at the carbonyl oxygen of aldehydes and ketones. The number one, the weakly basic carbonyl oxygen reacts with proton or Lewis acid. The protonated form of aldehyde or ketone is resonance stabilized. So it is more stabilized, more stable than a 3-degree carbocation. Okay, an aldehyde or ketone, let me repeat again, aldehyde or ketone, when protonated, okay, we get a carbocation, and that carbocation is more stable than a tertiary carbocation. Okay, this gives, why? Because of the resonance stabilization. Okay, this gives the aldehyde or ketone conjugate acid carbocation character. Let us see this one. This is what we are talking about. If a carbonyl compound is protonated, we get this one. Now this is what? It is having a resonance structure. This pi bond goes to stabilize the positive charge on oxygen, and therefore we get a positive charge on the carbon. Okay. So therefore, this carbon which is having positive charge is further more stable than a tertiary carbocation. Okay, let us see the next topic. The protonated aldehydes and ketones can be thought of as alpha hydroxy carbocation. So here we will call this as alpha hydroxy carbocation. When an alkyl group replaces as the proton, the alpha hydroxy carbocation is formed. Okay. Now, what is alpha hydroxy if not hydroxy alkoxy carbocation? Alpha hydroxy or alkoxy, this is alkoxy, this is hydroxy. Why this is alkoxy? Oxygen is bonded to an alkyl group, or we have a carbon which is bonded to an alkoxy group, and here we have the carbon with the positive charge, we are bonded to a hydroxy group. Okay, these two are more stable than a tertiary carbocation. Why? I've told you, it is always resonance stabilized, this is also resonance stabilized, whereas it is not having a resonance structure. Okay, any resonance is not happening here, it is only having a 3+ high effect group, that's all. Okay, whereas here it is having plus high effect group as well as a resonance structure. So it keeps the positive charge can actually be distributed between carbon and oxygen, and therefore it gets more stability. Stability of protonated aldehydes and ketones. Supposing you have an alpha hydroxy, you have already learned about this. Alpha hydroxy carbocation is we have done it. That is pinacol on rearrangement. We have taken a pinacol and this is been protonated, and this water molecule leaves, and this becomes a tertiary carbocation. Now here this is why it is going for a 1,2 methyl shift. Why? Because we have here alpha hydroxy carbocation which is more stable than tertiary carbocation. Okay, so therefore we have this type of rearrangement, and finally we get pinacolon. Basicity of aldehydes and ketones. Just see here we have taken we are comparing here the conjugate acid of aldehydes. This is the conjugate acid of aldehydes with that of a conjugate acid of an alcohol. We are comparing both. So this one is having a pKa of -7 and pKa of -2.5. Protonated alcohols are less acidic. You know, pKa is lesser, stronger is the acid. Okay, so if this is pKa is quite less, -7, this is bigger, okay, more than -7, it is -2.4, 2.5. Therefore, it is protonated alcohols are less acidic. Therefore, alcohols are more basic than ketones. So, therefore, alcohols are more basic than ketones. Now, you have to understand this. This is having a resonance stabilization, whereas this is not having any resonance stabilization. Okay, so If this is resonance stabilized, means what? It is more stable in this form, and this is the conjugate base will be more, more less base